Okay, hi there, welcome back again. And now we'll discuss the two remaining details for our footing problems. So the first one we'll discuss is the development length, or let's say the required development length. The symbol is L sub D. Okay, so the development length is actually the required length so that the steel and concrete will bond together, say bond together as a one unit. Okay, so for example, this is our concrete and this is our, let's say, our steel reinforcements, and note that we have these lugs here. So for example, if we are embedding this steel reinforcement in a concrete, then how much length does it need to be embedded? So for example, in let's say in beams to to columns, or let's just do example in the footing. Okay, so for example, in the footings, then we have this steel reinforcement. Now this steel reinforcement, then do we need to bend it, or do we need to provide a hook? So that depends upon the required development length. Now, for example, this is the embedment. Okay, and if this is our actual length. Now, if the computed required development length is greater than this one, let's say it's up to here, then we have to do a bending here, or let's say a hook. But if it's not, if the required LD is just up to here, then meaning that this one is enough. Now to solve for the for the development length, we have actually a conditions and that can be found in the NSCP. So for example, we have 20 bars and smaller. For this one, we have 25 bars and larger. Okay, so if you have a bar, referring to this bar, this is steel reinforcement, that's 20 in diameter and smaller, then meaning that our LD can be computed using these equations. So we have Fy times, I think this is xi or psi of d times psi of e all over 2.1 lambda square root of Fc prime times the bar diameter. And for 25 bars and larger, the equation for the development length is Fy times psi of t times psi of e, 1.7 lambda square root of Fc prime times the bar diameter. Now there's actually a description on where this applies, where this equation applies, and that can be found in our lecture handouts as well. Okay, and for other cases, then there's another equations that's to be used. Now let's discuss first what is this psi of t and psi of psi of t and psi of e. So psi of t is that's the reinforcement location factor, and this one is the reinforcement, or let's say coding factor. coating factor. So if there's paintings here, then you have to account for that coatings. Okay, so basically they're just factors, and the values of these factors can be found in NSCP. But in our course, since we're not going to delve into the details of this, but unless otherwise specified, then we'll just use y sub t is equal to 1, and this psi sub e is equal to 1. Okay, so if these parameters are not specified, then we'll just have to use the value 1. Okay, and then this lambda, you have already encountered this in some equations, and that's the concrete modification factor. And if our concrete is a normal weight concrete, then this lambda is equal to 1 unless otherwise specified. Okay, so that's our development length. Now, take note that this development length does not only apply to the footings. It actually applies to any reinforced concrete members wherein you have to provide the correct embedment, and for example in beams to columns, for examples. Okay, so now let's move on to the bearing capacity. Okay, that's the bearing capacity of column at base. Okay, so for example, this is our footing, and I'll draw it purposely in this rectangular shape. And it's like in an exploded view. Now we have the loadings. We have the loadings from the column. So we have these dead loads, and we also have the live loads. Now these loadings, they actually transfer the forces at this area, on this let's say column area below the column base. Now we have to check if the bearing capacity of the concrete is enough to handle these loadings. Okay, so the equation to check for the capacity, for the bearing capacity, is this equation. Okay, so let's say N is equal to the reduction factor times 0.5 FC prime times area 1. Sorry, this is 0.85. Okay, 0.85 FC prime times the area 1. So again, that's just the typical stress equations, wherein this is the stress, and this one is the area. So you have this bearing loads. Okay, so that's in N, and the reduction factor is, since this is compressive loads, then that's gonna be 0.65. Okay, FC prime and the area 1. Now what is this area 1? This area 1 is the area actually of the column, the cross-sectional area of the column. Okay, so this is it. This is our area 1. Now this capacity of this bearing capacity can be increased by a factor, by this factor. So that's the square root of a sub 2 divided by a sub 1, but it should be less than 2. Okay, so this is like our factor. This is our factor. Okay, so what this means is that if the area 2 divided by area 1, and we take the square root of that, and um, if it's greater than 2, then the value that we'll take, or the factor that we'll use, is 2. So meaning this is our upper limit. Okay, so what is this area 2? Now, area 2, it is defined as the area that is geometrically similar to the column area. So meaning if this is a square, then it's gonna be a square area as well in this footing, and this area should be at it's like we're taking the centroid. It's gonna be concentric to this column. Okay, so we'll take something like this. Let's say the maximum, since this is the centroid. Then let's say this is going to be the maximum dimension. And since this is a square, then we're going to have something like a square area as well. Okay, so it's something like that. Now, if our footing is a square, then that's just simply the footing area. But if our footing is rectangular, then you have to take um, these dimensions. Okay, so take note, this area 2 is the area that's similar in terms of geometry, similar to this area of the column. Okay, so if we take that square root of A2 divided by the square root of divided by this A1, then we solve that value, and if it's less than 2, then we use it. But if it's greater than 2, then uh, this 2 value will be our upper limit. Now, so since this is a capacity, then we have to solve it. We have to compare that to the loadings. Now, since this is a point load, okay, so let's say this is in Newton per mm squared times mm squared. So what you get is actually a concentrated loads. So we have to compare this bearing capacity to the factored loads that's also concentrated, and this factored loads be the dead load and the live load. Okay, so to solve these factored loads, we have to solve for 1.2 dead. We have to apply the combined load is 1.2 dead plus 1.6 live. Now, if n is greater than the factored loads, then no need to provide no need to provide dowels. Okay, so um, it's like a transfer steel. So it's a steel that's going to be provided to accommodate the extra loads. Okay, so no need to provide dowels, but if n is less than pu, then uh, provide dowels. Okay, so now let's go back to our problem. Okay, so now let's solve for the bearing capacity, or we have to check the bearing capacity. Okay, so first we have to draw again our footing, and we have this area. This is actually area 1, and this is our area 2. We have 2.9 meters by 2.9, and this one is 0.5 times 0.5. Okay, so now let's solve for for the bearing capacity. Okay, so let's just write N is equal to the reduction factor times 0.85 FC prime times A1. Now let's substitute the values. We have 0.65 times 0.85 times the compressive strength of concrete is 27.5. That's in megapascals times the area 1. So the area 1 is just simply, since this is in megapascals, then that's going to be 500 mm squared. Okay, so that's the area. If you do the math, what you get is 3798.4. And of course, if you use this, then you get a unit of newtons. And typically for concentrated loads, we use this kilonewton. Okay, so that's our capacity, but we are also allowed to multiply that to a factor. So we have to check. So let's say, checking now, or solving for factor. Okay, so our condition is that A1 or A2 divided by A1 should be less than 2. So if you do the math, if you substitute this 2900 times 2900 divided by this A1, then what you get is 5.8, and that should be less than or equal to 2. Now, since this is greater than 2, then therefore use 2. Okay, so now we'll multiply our N, 3798.4 times 2, and we get a capacity of 7596.8 kilopascals. Okay, so now let's solve for the factored loads. That's just 1.2 dead plus 1.6 live. So it's just 1.2 times our dead loads, 1,200 kilonewton, plus 1.6 times 1,120 kilonewtons. What you get is 3,233 kilopascals. Okay, so therefore, no need for doubles. Okay, so now the last one, we'll have to check the development length. Okay, so solving for LD. Okay, so our equation for LD, since this is 25 mm bars and larger, then our equation would be Fy times psi of t times psi of e divided by 1.7 lambda times square root of Fc prime. Okay, and this is the bar diameter. Okay, so that's if you substitute the value, this is 275 megapascals, and then this one is 1. Okay, otherwise specified, we'll use a value of 1. 1.7 times, again, that's normal weight concrete, and then square root of 27.5 megapascals. And the bar diameter of 25 mm. So we get a value of 771 mm. Now, if we draw this, let's say this is our let's say the critical section for flexure, and if we have this, let's say, steel reinforcements, then what is this length? Now recall, this is 1.2 meters. we have to subtract a concrete cover of 75 mm here, and then what's left remaining is actually greater than, okay, so the length is greater than the development length, so no need for bends or hooks. Okay, so finally we have to provide a summary, or let's say a drawing plan. So that's going to be a square footing, and this is our column, and of course we also have to provide an elevation view. Okay, and let's say this is our natural grade line, and okay, so if we specify the dimensions, then we have this thickness of um, that's 800 mm, and this distance right here, it's 1500 mm. Okay, and also we have to draw the steel reinforcements, so the ones on, okay, so it's something like that. And if we try to draw it on the in this plan view, then we have this bars like here. Okay, so we can specify this as 17 pieces of 25 mm bars both ways. And here we can also include a concrete cover, say 75 mm concrete cover. Okay, so the dimensions we have, okay, so this one should be this color, 2900 mm, or you can just use units in meters if you'd like. Okay, so 2900 mm. Okay, this one is this is 500. This one is also 500. Okay, so if we review what we did, okay, so this is our problem, and we're actually given with some details, and we assume a concrete height of a thickness, or let's say the footing thickness of 0.8 meters. So the first step is to solve for the effective pressure. So the effective pressure is just the allowable pressure, and this one is given from the tables, or let's say from the geotechnical report. So we minus that the pressure above, so the pressure of the concrete footing plus the pressure of the soil, and if we solve that, we get a 280.28 kilopascals. Okay, so if we illustrate that, this is our footing, and we have a loadings upward. This is our soil effective soil pressure, and this is our pressure above, the pressure from concrete and the soil. Now, since we have the effective pressure, then we can solve for the area of the footing. Then what's going to be the size, or let's say the area of the footing? And in this problem, we are going to design a square footing. So since we now have the area, then we can solve for the side. What's the dimension, what's the length, or what's the width? That's just simply square root of the area, and that's 2.87 millimeters. Now, if this is our width, or theoretical width, then we have to round it up to some um, to some reasonable values, and that's 2.9 meters. Okay, so take note that for the, or let's say in solving the area, we're not using the factored loads, we're just simply using the dead load plus the live loads. Okay, so now we have this. Then of course, if this is going to be our width, then our area, our actual area would be different. Okay, so now we're going to solve for the factored soil pressure, because we will use this in calculating the thickness, the footing thickness based on the shear. So again, we first solve for the area, and once you have the area, then you can solve for the footing thickness. Now this one, this h sub c, this is just an assumption. Now we have to check this assumption. So that is why we have to calculate the thickness in terms of the shear. Okay, so for the one-way shear, and recall that one-way shear, this is the critical section, and we solve for the capacity of concrete and then the factored loads. And when solving that, we obtain a value of this depth, and we have 438 millimeters. So we still have to check that check the thickness in terms of the two-way shear, because what if the footing will fail in this manner? So what's going to be our minimum depth, so that it can prevent the failure. Okay, so it's just the same process that we solve for the factored loads and then the factored capacity, and compare that. Actually, not compare, but rather equate that. So once you equate this, then you do the math, you can actually obtain a value of this depth. Now, the depth that we'll use is the maximum of the two. Okay, so here, that's gonna be the 525 or 526 millimeters. Okay, so the next step that we did is to solve for the flexural capacity. Now we already have the thickness, we have the area, and now we have the thickness. So the next step is to solve for the required steel area, so that we can determine how many number of bars that we're going to put in our footing. Now in illustration, the flexure capacity, or in solving this flexural capacity, we have this critical section at the face of the column. Now if you're having a rectangular, let's say rectangular footing, then you have to solve for the other side. But here, since this is just a square footings, then it's just the same. Now if we solve this is our loaded area, and we have to determine this distance, and this distance is just 1.2 meters. Now, so take note, this is our soil pressure, our factored soil pressure, and if you take the resultant or something like that, then the moment arm would be at the centroid, just at the midspan, so that's x over 2. Now having this, we can now solve for the factored loads, and we use this equation: the pressure times the area, okay, times the area times the moment arm. So we have this 801.79 kilonewton meters. Okay, so sometimes we're using units in Newton mm, and sometimes it's in kilonewton meters. But typically for loadings, I mean, this one is more common. But for the strength side or resistance side, this one is more common. Okay, so now we have this factored loads, then we can solve for the nominal capacity by dividing that to our reduction factor, assuming that it's 0.9. Okay, so once you have this nominal capacity, then you can actually solve for the steel ratio. And once you have the steel ratio, then you can solve for the number of bars. But just a couple of notes, this D in this equation, the effective depth, that's not the depth that we solve. Actually, we still have to add the distance from the centroid of these top bars, because we're going to have um, reinforcements in both ways. So we're going to add this distance, which is just 1.5. So that's 1 times half, I mean plus half of this bar diameter, and that's going to be our d. So if we solve all the way here, including the concrete cover, then we have to check if our actual height or thickness of footing is less than or greater than to the assumed. Because if it's greater than, then we have to redo our calculations. If not, then we can just leave it as it is. Okay, so this is now our AS, minimum steel area, and we have to check that. We have to check this theoretical steel area to our minimum. And now we can solve for N. And after that, we check the bearing capacity of concrete. Okay, so we solve for the bearing capacity, and then we multiply that to our factor. Then we compare this bearing capacity to the factored loads. Now, if the capacity is greater than the loads, then you can just, there's no need for towels. Then the last is to solve for the development length. Now, since our bar is 25 mm and larger, then uh, we have these equations. Now, as I've said, unless otherwise given, these factors, these coding factors and location factors, if they're not specified here, just use the value of 1. Okay, and finally, don't forget that you have to provide something like a summary on this design, on this footing design. Okay, so this is our last topic in the reinforced concrete structures, and in our next videos, we'll move on to steel structures.